Betelgeuse is a really fascinating star. Not only does it possess a fantastic name, but it's one of the nearest red supergiants to us. That is to say that although it is cooler than most types of star, it has a massive diameter. If it were the star of our solar system, everything up to the asteroid belt would be inside it. It's roughly 700 light-years from us, much farther away than most of the other visible stars. But since it's so large, it's the 10th brightest naked-eye star in the sky and brightest in the infrared. It can be seen readily as the left shoulder of Orion. If you do try to find it in the evening sky, it is also perceptibly redder than any of the stars around it, and it twinkles a lot. There is also something quite extraordinary about Betelgeuse. It's going to go supernova a tiny second. I say that in astronomic timescales, that is still 100,000 years. How do we know this? Well, you see, big mass main sequence stars, or stars in the adulthood stage of their life, are driven by the nuclear fusion that continues inside their center, transforming hydrogen into helium. This fusion produces an internal pressure, which fights the action of gravity that desires to pack the star into a lesser volume. But ultimately, the hydrogen fuel inside the core will be depleted, having transformed into helium. Thus, the fusion process halts and the star core cannot resist the pull of gravity any longer. The core becomes compressed, but if the star is large enough, the compression will reignite fusion. This time on the helium in the core into heavier elements such as carbon, with this process being repeated for oxygen and neon. With each renewed cycle of fusion, the star's internal pressure makes the diameter of the star grow until it starts the red supergiant stage of its life, when the core is being turned primarily into iron. Red supergiants can't fuse anything above iron. So when the fusion ceases, the star collapses entirely into a supernova. And that's where we're at with Betelgeuse. Now we are waiting for this last collapse. Whenever it does explode, it will eject its atmosphere far into space, which will be visible in our sky for a good 2 to 3 months before it dims again. It is far enough away that no harm will be less on Earth. But it will make quite the spectacle, perhaps being as bright as a full moon, so even visible during the day. Now something else rather fascinating has been happening with Betelgeuse. It's made the headlines extensively, such as in 2009 when it shrunk by 15%. You'll also have heard this year that Betelgeuse has been fading, and scientists hadn't really figured out why. Speculation was rampant that this might be a sign of this predicted supernova, though perhaps tragically, this is probably not true. New information from the Hubble Space Telescope has indicated that the star itself is not necessarily dimming, but rather that there is some dust that was expelled from the star and cooled, blocking the view. In September of 2019, Hubble traveled through warmed material sweeping away from the star's atmosphere. During the next several months, this material had been seen close to the star. By December, the star started fading in its southern hemisphere. It's speculated that hot carbon was in the outflow, and as it traveled around the star, it was expanding, and this cooled it off. When we were last seen, it didn't move away from the star, but crossed over our observation of Betelgeuse. At its brightest, Betelgeuse was 2-3 fainter than it should have been. However, ever since April 2020, Betelgeuse has actually returned to its normal brightness. So this cloud has either moved out of the way or totally dispersed. So maybe this wasn't the exciting conclusion to this story you were looking for. Probably no supernovas for a while yet. But maybe that's a good thing because after the event, Betelgeuse will no longer be visible. Supernova remnants. Observed by Hubble. The item is really a spire of cold gas and dust, a part of the Eagle Nebula Stella nursery. The spire stands at a whopping 9.5 light-years tall. The spire itself is being dissolved by thousands of hot young stars in a cluster just off the picture. This haze surrounding the building is hydrogen gas being evaporated by ultraviolet radiation. while the black areas are more compact, resistant gas. This activity may well be creating additional stars as well, since seen here with the bright heated gas pushes against the dark, colder gas. This pressure may well cause stars to form. Stars are also formed within the tower where dense gas collapses under gravity. These bumps may appear small, but they are actually the size of our entire solar system. These stars will continue to grow as long as there is gas around to feed it. The background of the image is more distant lighted gas. Blue is ultraviolet light colliding with oxygen, and red is hydrogen. NGC 346. We're now moving 10,000 light-years away to a satellite galaxy of ours. The Small Magellanic Cloud, NGC 346, is one of the most dynamic and highly detailed star-forming regions of known space. At the center of this region is a bright and intense group of stars, surrounded by a jagged arch of dark, cool gas. As in the previous image, the UV radiation from these stars is pounding on this gas structure. You can see the wind trail left behind by these denser globules. This star cluster also contains the brightest star within the Small Magellanic Cloud. Number 13. The Crab Nebula. This nebula is the remains of a star which exploded in a supernova. Interestingly, it is recorded that early Japanese and Chinese astronomers saw this explosion in 1054. What you are seeing here is the remnant of that star in the form of mostly hydrogen gas. Faintly visible in the center of this photo is a neutron star, the incredibly dense core of the exploded star. It is only 30 km in diameter and spins an incredible 30 times per second. As it spins, it emits two beams of high-powered X-ray beams into space. This is why when you look at the star, it appears to be pulsating. This star is responsible for the bluish color of the nebula. Number 14. The Orion Nebula. I have to say, this is one of my personal favorites pictures Hubble has ever published. The colors are beautiful. It should be hanging in an art museum. And there's so much going on. The Orion Nebula contains approximately 3,000 stars, some of which weren't uncovered until this photo was taken. Four largest stars in the nebula are in the center of the bright area, formed in the shape of a trapezoid, and they're well named the trapezium. Surrounding these stars are very young stars that most likely still retain their protoplanetary disks, as you can see here. These condensing gas disks may quite possibly develop into planets one day in the future. Up at top left here, we have one star lighting up the nearby dust, an area known as M43. We have denser gas that resists erosion by UV light and gas responding to it. You can actually see the bow shock from certain stars as they resist the stellar wind of the largest stars. On the left is a cavity wall of the nebula. And interestingly, the dim red stars you see here, these tiny pixels really are brown dwarfs, sometimes referred to as failed stars. Brown dwarfs are stars that cannot sustain nuclear fusion in their cores, like our sun does. As a result, they're comparably cool, less massive, and not as bright. And finally, the Orion Nebula is our nearest star-forming region, and is well over 1,300 light-years away. Number 15. The Pinwheel Galaxy. A break from nebula now, and something much larger we are looking at. The pinwheel, also referred to as M101, is classed as a grand design spiral galaxy. The photograph itself is massive, and we can take a detailed journey from one side to the other. It is a reasonably close neighbor galaxy tour, OWN being only 21 million light-years away, and is also a similar size to the Milky Way. It has very distinct arms and an unusually high ratio of star-forming regions for a galaxy seen where the colors are strongest. This means it's a really active galaxy. The reason for this is due to exploded stars, superheated material, and gas plummeting toward black holes. Number 16. The Cigar Galaxy. Also M82. This incredible starburst galaxy is striking for It's expelled flame-like red hydrogen gas, young starsair forming 10 times more rapidly in this galaxy than within our own Milky Way. This is believed to be due to UF encounters with its near neighbor M81. They are only 300,000 light-years away from each other, and due to their massive gravity, they have these tidal influences on one another. M82 contains the brightest known X-ray pulsar named M82X2, the large pink dot in the center of this image. It's baffling astronomers because it's emitting 100 times as much X-ray radiation as something of its mass should be capable of do. For comparison, X2's binary system partner M82X1, the pink dot to the bottom left of X2, is a black hole, but unexpectedly, it radiates less X-ray radiation. Number 17. Cassiopeia A. This is the colorful remnants of a supernova explosion of a star. It is the youngest supernova explosion remnant in our galaxy, and is only 11,000 light-years away. The light striking Earth from this explosion would have occurred some 300 years ago, though there's no report of any observations. This shell is roughly 10 light-years wide by now. Number 18. The Lobster Nebula. It's another stunning nebula located in the Milky Way around 11,000 light-years away from us. It also has a lot of protostars discovered with dark disks and cocoons of gas hiding the star's view. This star cluster is called Pessimist 24. Pessimist 241 was believed to be the largest star ever at 300 solar masses. Turns out, however, this is really a multi-star system and is actually at least 3 stars each, approximately 100 solar masses. Even with this decrease in size, however, they remain some of the largest stars that we are aware of. Number 19. NGC 60. This image is not only stunning for its oranges, blues, and shapes, but also due to all of the galaxies in the background. The reason why these galaxies are so visible is because NGC 602 is located off-center from the Small Magellanic Cloud, so there's not so much stars that get in the way. This also makes the nebula considerably easier to study. In the middle is a group of young bright stars eroding the dust walls away. And last but not least, Number 20. NGC 672. This is the final photo for this episode. And what we have here is a barred spiral galaxy. It has these 2 arms which extend away from the rest of the galaxy, Theone on the left being much more prominent than the other. This galaxy actually has 4 arms, the last 2 isolace-specific, and they're hidden away within the galaxy. And interestingly, the arms don't connect at the nucleus, but at the tip of this straight bar of stars. This is precisely why it's called a bar spiral galaxy. In the vicinity of the bar, the galaxy's undergoing starburst, a huge level of star formation. NGC 1672 is a whopping 60 million light-years away. Black holes are among the most mind-boggling things about space. The weirdest dead stars. Black holes, to begin with, they aren't objects. They're a product of the intense bending of space-time. And due to this bending, some very strange things begin to happen around them that will alter your understanding of the way the universe revolves around you. Some of it is so bizarre that possibly you might not believe it was real if it were not for the firm math that supported their being and attributes, and the growing evidence that the math works through observations in our own universe. And in this series, we will venture into the unexplorable. Come with me on an exploration as we try to get some grasp on the strange science of how a black hole is created, what happens around it, and in the next episode, research what could actually provide an exit from the most inescapable prisons in the universe. I hope at the end of this video to have gained your like and subscription. Black holes exist in sizes ranging from the very small to the incredibly large. The smallest black hole we have ever seen is 3.8 solar masses. At the other end of the spectrum, we have black holes which have been around since nearly the beginning of the universe, billions of solar mass black holes. These bears are not just huge, they are enormous. They would fit comfortably in the entire solar system within their event horizon. Black holes formed today are the last step in the life processes of especially massive stars. When a star of this sort is born, it is really equilibrating under the pressure of two forces. The first is gravity, forcing its mass to center itself. Down in the depths of the star, hydrogen atoms are pressed against other hydrogen atoms with such pressure that they bond together to create a heavier element, helium. This new atomic configuration actually requires less energy than it did when it was two separate individual hydrogen atoms. So the excess energy that is left over is released. This released energy is the second force. It radiates back out from the core of the star as heat and light, balancing the pressure of gravity pulling in. At this point, the star will be relatively stable until the reaction starts to wind down as it exhausts its hydrogen fuel. If the star is large enough, once hydrogen starts to be depleted, the star will fuse the recently created helium into yet denser substances such as carbon, not neon, and then oxygen and silicon. But then it starts fusing iron. The problem with iron is that it doesn't store any energy in its new state, so has no excess energy to let off. It simply sits in the center of the star, expanding. With no energy fighting against gravity, very soon, the balance tips. The energy of this collapse is astounding, but the force is dependent on the original mass of the star. Like a hammer striking on an anvil, the mass of the star rushes down to meet the core with such force that the rebound of that blow is what we call a supernova. Matter and energy are blasted out across the universe from the crackback in one of the largest explosions possible, which produces elements even heavier, more than iron, all the way to uranium. And what is the star left with? Well, it depends. If the mass of the star and therefore the force of the impact was too low, what is left behind is a neutron star. A tiny sphere of matter at most some 25 kilometers in diameter, and yet so tightly packed, with mass that it weighs 1,000,000 Earths. But if the mass and therefore the force was large enough, physics as we understand it collapses down, and we are left with a black hole. When you look at a picture of a black hole, the black ball you are looking at isn't actually the black hole. Scientists think a black hole's real shape is likely even smaller and more dense than a neutron star. In fact, it is most likely infinitely small and infinitely dense, a singularity that radiates forces which distort time and space itself. But we don't know. And why we don't know is due to something known as the event horizon. Everything with mass has gravity. We've been aware of that since Newton's time. But then in 1915 came Einstein, presenting his theory of general relativity, and a contemporary of his by the name of Karl Schwarzschild deduced from it that there might be objects so heavy that they would generate enough gravity where even light itself would be unable to escape. And if even massless photons of light could not escape, nothing would. When you glance upon a photo of a black hole, you're not actually looking at the black hole. You are viewing the event horizon surrounding it. The demarcation line where gravity has gotten so strong that light can no longer escape. There is nothing but darkness. Now, its impact on space is one thing, but black holes also affect another facet of the universe, time itself. You see, according to Einstein, space and time are inextricably linked and mass warps space-time. With the singularity's point of infinite mass, it stretches space-time so much that the event horizon also represents the place where time would cease to exist. Inside the event horizon, space and time essentially do not exist, a location where there is no where or when. This creates an amusing sight to an external observer witnessing matter entering a black hole. From their viewpoint, as matter nears the black hole, it will slow down until moments before the event horizon, where it will freeze altogether. You'll never see it pass the event horizon. There won't be any gratifying absorption. Rather, the matter will just fade away until you can no longer view it. When originally theorized, Astronomers and physicists weren't sure whether black holes existed or not. It took 40 years later to discover the first evidence of a black hole. In 1964, scientists utilized newly developed X-ray satellites. Astronomers saw an object in the Cygnus constellation that appeared to be radiating a lot of X-rays. Oddly enough, though scientists were unable to detect the object itself. It caught them by surprise because if it were a star, it should radiate visible light in addition to X-ray radiation. They found that this unseen object was 15 times more massive than the Sun, and the densest neutron star was 3 times the mass of the Sun at most, and so scientists knew that this was probably the first black hole discovered. And since then we've seen lots of black holes. Huge ones appear to be in the center of galaxies, and we've even been able to photograph some dark blots against a spinning ring of matter that embrace them and fall into them, their accretion disk. This is how black holes can still be seen through X-rays. Although black holes can't produce visible electromagnetic radiation themselves, the X-rays emitted from them actually come from the accretion disks, wherein falling matter is heated to millions of degrees Celsius due to intense friction. Black holes without infalling matter are essentially invisible with nothing to see, but no bright accretion disk to find. Black holes are still an emerging area of physics, and there is still so much to learn. From what we've learned up until now. You might be asking yourself if a black hole can ever cease to be a black hole, or will it just keep growing until there is no matter or radiation anywhere in the universe? It would appear so. But in 1974, in his paper titled Black Hole Explosions, physicist Stephen Hawking theorized that there actually existed a means whereby energy, and therefore mass, could escape from a black hole. But in order to explain why, we need to delve into some really bizarre theory. We must study some precepts of quantum mechanics. But first, let me pose you a tough question. What is nothing? Envision for a moment a patch of space with nothing in it. There's no space dust atoms, not even radiation traversing it. As close as one can tell, there's nothing in it. And yet, is there actually really nothing there? Something at the root of things is present here. And we can be certain that this is so when a beam of light passes through it. If you know the characteristics of light, you'll realize that light is really waves of magnetic and electrical charge that are streaming along with each other in a straight line. But let's examine that term wave. A wave in the sea is the passing off energy traveling through water. If you were to view a single particle of water, it's 24/10 not really moving anywhere except round and round. And yet because it transfers energy to the surrounding atoms, energy does travel to the shore in a perpetual motion that reaches all the way to the beach. Likewise, a sound wave travels by transferring energy from air particle to air particle, with each particle moving just a little bit, getting energized, and then transferring that energy to the next particle in sequence. But in our vacuum of space where there's nothing in it, where our photon of light is moving in waves, have you ever taken the time to ask yourself what precisely is waving? This points towards a fundamental something that exists even within nothing, a fabric that constitutes all of reality itself. Quantum physicists refer to this something as a quantum field. Quantum fields are difficult to get your head around, but they're inextricably relevant when it comes to the fate of a black hole. And this is something I hope you'll come along with me in the next episode for, where I will discuss this at length and hopefully not in a way that demands a degree in astrophysics. Did you ever wish that you might witness a supernova close-up? Although we don't exactly the star that cannot be killed hope for that in 2024, you will get to witness what is perhaps the next best thing, namely the blast of the blaze star. And amazingly, it just keeps bursting. Some time ago in May 1866, on a partly cloudy West Irish spring evening, amateur astronomer John Birmingham traveled home in the dark on the stroke of midnight. He slowed his pace at times so he could glance upward at the stars. With his keen eye, He scanned the evening sky for constellations he knew like 1,000 times before. As his eyes approached the northern crown, he halted, amazed. There was a bright new star in this familiar constellation. He had witnessed a recurrent nova in Thebanary star Tone Borealis, affectionately known as the Blaze Star, an explosive astronomical phenomenon that occurs once in a lifetime. This phenomenon would assist in revolutionizing our knowledge of nova events and define the field of stellar astronomy in the next decades. And for those of us living in 2024, we will have the exclusive chance to witness the same recurring nova explosion that enthralled Birmingham's interest over 150 years ago and that chilly spring evening in Ireland. And you won't even require a telescope or any sophisticated equipment to view it. Why is it going to occur once more? And when is it going to occur? Welcome aboard as we get ready to witness this remarkable stellar phenomenon. The BL star nickname is somewhat misleading because it's actually a binary system of two stars bound in orbit with each other, and it's the interaction between these two stars that makes the nova explosion every 80 years or so. Actually, it's estimated that some 50% of the stars we observe are not alone, but multiple star systems. Both of the stars in the binary Blaze star system began as average-sized stars, like our Sun, but everyone is at a very dissimilar point in their life cycle. Small and mid-sized stars typically evolve along the same path as our Sun. At 4.66 billion years, our Sun is a middle-aged, average-sized star. In 5 billion years, it will exhaust its supply of hydrogen fuel and start fusing heavier elements, growing into air giant that can grow so large it engulfs Mercury, Venus, and possibly even Earth. When their giant depletes its last bit of fuel, in anywhere from 5 to 10 billion years, it will finally shed its outer shell, leaving behind a nebula of gas around a white dwarf, the extremely dense and tiny core remains of the now behemoth star. White dwarfs are sometimes referred to as dead stars because they have no fuel left and will take the next 10 trillion years to cool off until they cease to give off heat or light. Both binary stars in the Blaze star system are average-sized stars along the same path, but they are further along in their evolution as stars than our Sun. Indeed, this is the very reason we will be able to see the recurring nova in 2024. And it all depends on the way these two stars interact. One is a red giant and the other a white dwarf. As the red giant is heated and expands its outer shell, it is being stripped of hydrogen by the immense gravitational pull of its neighboring white dwarf. Over time, the white dwarf collects this material on its surface, kind of like a cosmic vacuum cleaner, causing a buildup of pressure and heat. Eventually, this buildup becomes too much and causes a thermonuclear explosion that blasts away all of that built-up material. Picture the white dwarf like a party popper. You keep tugging the string tighter and tighter, growing tighter and tighter, and then you pull too tight and it snaps, spewing confetti everywhere. That's sort of the pressure and heat that accumulates on the Blaze star's white dwarf until it finally reaches the breaking point. The outcome, a nova explosion so energetic it can make the Blaze star shine 1,500 times brighter than normal, about once every 80 years from Earth, 3,000 lightly years out. Now, how is this unlike the better-known supernovas? Although the Blaze stars have a huge explosion every time it has a nova, a so-called classic nova, it doesn't blow up the white dwarf where it happens. Rather, it just shells off material gathered from its nearby star occasionally when pressure and temperature get too intense, and it just happens to be close enough to us that we will see a radical shift in its brightness from Earth. Conversely, for an isolated star to annihilate itself upon its death by detonating in a grandiose supernova that can be 1,000,000 times brighter than the Blaze nova, it must begin with over 8 times the mass of our Sun, far more massive than those in the Blaze star. The nearest star on its way to a supernova explosion in the near future is the red supergiant Betelgeuse, a star that normally rates as one of the 10 brightest in our night sky, even though it's 640 light-years away. And by soon, I mean in cosmic terms. So don't be alarmed. Scientists don't foresee this star as a supernova for tens of thousands of years. On cosmic timescales, that's the blink of an eye. On human timescales, not quite. But just for an instant, picture the breathtaking spectacle that any person on Earth would behold as Betelgeuse detonates in a supernova. Once the initial blast occurred, the star would shine like a full moon and be seen during the day. How beautiful that would look. But although immensely uncommon, Betelgeuse will not be the first time humankind has observed a supernova. And the blaze star is far from being the solanova of recent times to be seen with the naked eye. The earliest recorded supernova, now called SN 185, comes from Chinese astronomers in 185 Adwen. They recorded what was called a guest star, which appeared in the night sky for a staggering 8 months. Modern astronomers have been able to find the remnants of this explosion to confirm that it was, in fact, a supernova. There have only been a handful of supernovae that were visible with the naked eye in recorded history. One of the famous instances, and the most recent, was in 6004, when the German astronomer Johannes Kepler recorded a supernova which was so intense that individuals were able to view it during the day. What we will witness in 2024 will be among the brightest classic nova of this century. And just like a supernova, this is a rare and significant phenomenon. Classic novas that can be seen with the naked eye happen comparatively often, at least in contrast to supernova. But even though these traditional nova can be seen in our evening sky roughly once a year or two, they never become bright enough for the inexperienced or unadulterated eye to catch. The blaze star, however, should be one of the most brilliant traditional nova to be visible in our evening sky in close to 50 years. In astronomy, a star's brightness, as seen from Earth, can be measured on a scale of apparent magnitude. The smaller the magnitude, the brighter the star. So a star with a magnitude of 0 is brighter than a star with a magnitude of 1. Star with a magnitude of 1 is brighter than a star with a magnitude of 2, and so on. Typically, it takes an apparent magnitude of about 6.5 in order for a star or planet to be visible to the naked eye on the darkest night. For some perspective, the 7 stars in the Ursa Major constellation, also known as the Big Dipper, have apparent magnitudes ranging from 4.8 to the brightest, at a magnitude of 1.7. The brightest star in the night sky is Sirius with a magnitude of 1.4444, and the daytime sun has a magnitude of 26.5. Yes, the scale of apparent magnitudes does go into the negatives. The blaze star has a magnitude of typically 10 and cannot be seen with the naked eye from Earth. But in the nova explosion, every 80 years, this star reaches a magnitude between 3 and 2, making it shine from seemingly out of nowhere to one of the brightest stars in the heavens. Peculiarly, the word nova is derived from a Latin term nu, and I suppose prior to telescopes, it would have been a surprise to view a new star where none had been before. More recently, Nova Century 2013 caused astronomers surprise in being among the brightest in more than a century, with a maximum magnitude of 3.3. The blaze star nova last burst in 1946 to a magnitude of 3. This year's display of the blaze star, however, promises to be even more luminous than that, and could reach an optimum magnitude of 2, which would put it on a par with Polaris, the North Star, which has a magnitude of 1.97. But this celestial spectacle will not endure long. Once it erupts with the nova explosion, the blaze star may only be visible to the naked eye for a few days or a week before it fades back into the darkness. There is no exact date when it will happen, but scientists predict it may happen any day now, going into the second half of 2024. Be sure to keep an eye on the news and the sky to see when the nova explosion starts. In order to locate the blaze star in the evening sky, look for the two adjacent constellations of Hercules and the Kite form. The blaze star will appear in a tiny semicircle-shaped constellation named the Northern Crown, situated between these two larger constellations. If you draw a line through the Northern Crown, beginning with constellation, and last on the side nearest Hercules, the blaze star must be below the most southern of the northern 3616 Crown's last star. And if you have a good amateur telescope or can go to 3621 an observatory, you might even be able to see this binary star before the 3626 nova starts, so that you can really compare. These nova make us realize that even stars, 36, 33, which can appear eternal and immobile, possess surprising life cycles that may involve extreme transformations and spectacular dramatic explosions, such as a fireworks display in the cosmos. Infrequent and wondrous, every nova gives astronomers a special chance to collect observations that will assist in the improvement of our knowledge of stellar evolution, binary star systems, and stellar explosive phenomena. This nova will be one of the most thrilling astronomical events that we're going to witness during our lifetime. So keep a lookout for the night sky and perhaps feel just that little bit more fortunate to be alive and to have the chance to see this here on Earth. Have you ever observed a nova with the naked eye before? Do you have any special plans in place for when the blaze star nova begins? Until next time, keep looking up, stay curious, and let me know your thoughts in the comments below. Thanks for watching.